right, ladies and gentlemen, hello and welcome back once again to the briefing room. Yours truly, Eric Kavanaugh, is here, and this is going to be a fun show, folks. I get very excited, as you know, about technologies. I get especially excited about technologies that solve previously intractable problems. And I can tell you that data access, data movement, is one of the longest standing challenges in the world of data. That's true for data science. It's true for all structured data. It's true for unstructured data, which is 80% of the data in the enterprise. And no one has been caring about that until recently with large language models. And now it's like the race is on. So a quick nod to Future Proof. Check your local listings. The world's first made for TV webinar series. It's all about how today's technology designs tomorrow. And let's jump right in. All access past the end of data silos. Doesn't that sound exciting? So our speakers today, yours truly, along with David Flynn, CEO of Hammerspace, Molly Presley, CMO of Hammerspace, and Trond Myklebust, CTO. You've got an all-star cast here. Let me just give some history and give my thoughts, and then we'll get into the deep technical stuff with the team. So the history of data, think about it. You used to chisel data in stone, right? Like a legacy system. It's chiseled in stone. You're not going to get rid of it, not without great effort. We used punch cards in the 1800s, and my business partner years ago, Dr. Robin Bloor, once said that data has always been an afterthought in computing, which is kind of an interesting concept. Remember, we used to keep all our data on floppy disks. You used to keep the OS on a floppy disk in the original computers. And then in the 20th century, of course, file systems arose and different operating systems. I remember you'd go to buy an application, there'd be 8 different Windows OSs to choose from in Mac OS and Linux. It's like, yeah, that's kind of a pain. And then the network was born. Okay, open doors to move data around, but also a lot of complexity came out of that. So because of all that, we've had lots and lots of workarounds to get to the data we want when we want it that causes all kinds of other challenges. So back in my previous life, I used to do print production. And in the 1990s, you would have to get a SyQuest drive and a big old honking SyQuest disk that you would put these files on and then take it down to the pre-press folks, hand it to them. Not terribly efficient. And I started thinking, I'll be writing about this over the next year or so. Old IT versus new IT. And what does that really mean? Because you have this whole legacy landscape of technologies, of methods, ETL, ELT, all these different ways to move data. And I realized that old IT is imperative. You give detailed instructions for every single task. You hack out the code one line at a time, do this, do that, do something else. Old IT is also largely inside out. So you deploy a solution somewhere in your data center, then you work to connect it to everything that's on the outside. And most importantly, old IT kind of takes a long time to get up and running, at least in MVP. Think about 15 years ago with the data warehouse. You're talking 6 months to a year to launch an enterprise system. You just can't do that anymore. There's not enough time. The world moves too fast for that kind of approach. So new IT, I would say, is declarative. So you give it a desired goal and let the system figure out how, and then ideally learn from what it did, watch what it does, have some machine learning in the background to capture that and figure stuff out and document and go, aha, it was better to do it this way, because sometimes you'll just miss stuff. You'll just get the wrong idea. You don't know why. And to let the machine do that work for you is pretty clever stuff. It's also outside in, so you want to pull data from existing channels and use that to define your models. And new IT gets rolling much faster. You do need some checks and balances for accuracy, especially with generative AI. So just kind of keep that in mind. I love this. When I talked to the folks from Hammerspace and realized that they went and grabbed some developers from the Linux kernel, I was blown away. I was like, that's awesome. We keep hearing about shift left, and shift left means basically going upstream to solve problems way upstream before they get downstream and cause many kinds of problems. They call that error propagation in certain systems. Well, you can't shift any further left than going into the operating system, and we'll talk about that on the show today. So now imagine a parallel universe, a parallel file system where all your data is immediately accessible. No more waiting minutes, hours, or days for big files, complemented by an audit trail that shows which data went where and when. Doesn't that sound nice? You're solving countless problems at the source, which I think is brilliant. So with that, I say don't bring in the big guns. Get people to help you out with this stuff. Molly, or take it away.
All right. So thank you for the good introduction. And really, pictures weren't necessary. I am actually sitting next to one of those Linux guys. We're next to each other in the same room together. So we'll have Trond talk a little bit about what we're doing in the Linux kernel. And, when you think about what we're announcing today and how we can cover it all the way from the strategy from our founder and CEO, David Flynn, to the business benefits that I'll cover, and then how it's really implemented in our technology. We'll be covering kind of all those corners. So today, Hammerspace announced a new innovation in our data platform. And before we jump into what that is, I want to just give everyone a quick kind of high-level overview of what problems Hammerspace has tackled and kind of why we've done it. So if you think about the last 10, 20, 30 years, and Eric and I have talked about this on my Data Unchained podcast, and you think about what we've been doing, the architectures a while back over the last couple of decades were really designed for the storage system owning the data and dictating how it's retained, protected, and anything that was done outside of that was done outside the storage system, which meant you had to make a copy of the data to move it to another application, make a copy of the data to get it into the cloud. And that really created not just copy proliferation, but users didn't necessarily have access to or visibility into all the data that existed as it became increasingly decentralized. And so with Hammerspace, a kind of core innovation we had was moving the file system up the stack. So instead of embedding it in the storage system, in the storage hardware, we've raised it above the stack so that when users and applications connect to their data plane, to their file system, they just do that once. And if additional data sets are added, if additional data locations are added, different storage tiers are added, given if the user application has the permissions, they can immediately see all of the data in their global data environment. And so that gives visibility to the entire data set on a global level in all different types of storage environments and storage tiers. And then when the data needs to be moved, we aren't making copies. We aren't adding to this problem of copy proliferation. Instead, through intelligent automation, it is placed where it needs to be used. So if you have remote GPUs or you're spreading your data across compute clusters, the data is automatically orchestrated to the compute. If you need to tier it for disaster recovery reasons or lower cost storage reasons, that's also automated, but what is done under the file system so that the users and applications have a persistent view to their data. Even if it moves around, they can still connect to it, they can still see it as just a file directory path on their computer, and it doesn't disrupt their operations. And then underneath that then comes the storage system, and the storage system that is already in place or new storage that needs to be added can automatically be added as capacity or performance into that global file system, again, without disrupting workloads or users. So what that ends up looking like from a Hammerspace perspective is all the things that you need are buried underneath the global file system. That's a parallel file system. So you have the ability to deliver those HPC types of performance with metadata taken out of the data path. So you have a really high performance parallel file system storage infrastructure. Underneath that, if you have enterprise features that you need to take advantage of, to protect against ransomware or, encrypted data, be able to audit what's happened with data as it's moved around, that's all built in. And then, as I mentioned, the automated data orchestration makes it possible that as data needs to be moved for any purpose, whether it's to get it local to compute or for storage reasons, that's all done transparently to the user. And so I bring this all together, and it really touches on what Eric was talking about, that as the needs for data have evolved and organizations are trying to tackle that problem of the 80% of their data that's unstructured and gain visibility into what they have, knowledge about what is that data with enriched metadata, and then put it to use, you need to unify it into a data platform that has the ability to create metadata, unify access, and then place the data with the applications. And so that's what Hammerspace does from a very high level. And then before I hand things over to David to talk about what we are announcing today, I think it's always nice to see kind of a less complex view of, okay, that sounds cool. There's a lot of technology built in. What is the experience? And what it really comes down to is users have seamless access to their data. They're on their laptop, they have a directory tree, they can see all the data that they have permissions to see, that's sitting on their Isilon, their NetApp, their object store, and their cloud environment, for example. And it just looks like a directory tree. They can click on it, they can read, write, collaborate, and it's the experience that they're accustomed to with their file data. And it can be file or object. I'll mention that, and we'll touch on that more later. From an administrator's view, they have that single pane of glass to be able to see what is the performance of my overall environment. Are there mobilities of data that are going slow and why? So it's a really unified view of the data and the infrastructure to make it much easier to tackle this decentralized data, that unstructured data that's growing so quickly. Um, Today, we're announcing a new capability, though, that up-levels this both on the performance as well as the efficiency side. So with that, I'm going to hand things over to David to talk about what is Tier 0.
So yeah, let's start with the problem statement. What we have learned is that it's very common for folks to have high performance flash storage, NVMe, inside of their compute nodes or GPU nodes. And that it takes, sort of unrelated but related, is the fact that once you deploy a GPU cluster, it's not uncommon, as Eric put it, for one to realize that, oh, we need the storage subsystem. And then you have to take the time to deploy to create a shared storage environment from that. So key things here, it's time to market is critical. As soon as the GPUs are there, the clock is ticking on getting value from them. And yet here we have storage that is trapped capacity inside of the DGX nodes. And that storage largely goes unused because it is difficult to manage little islands of data inside of each server, isolated from the others, and especially in large clusters where you have tens, hundreds, or even thousands of these, like some of our clients do. It's very difficult to get any utility from the local flash. That local flash can come in very large quantities. It's not atypical for those servers to come with 30 to 60 terabytes baseline built in that you can't even opt out of in the bill of materials. Moreover, there are slots for up to 8 NVMe devices in each of those. So what Hammerspace Tier 0 does is it allows you to orchestrate, place, and access data across that server local NVMe from a global network shared file system, and do that using the hyperscale NAS architecture with the control plane that sits off to the side. So here is a visual of that. What this does is it unleashes that stranded capacity that's sitting in those servers. And it allows you to improve ingest performance, checkpoint performance, transform performance, how fast you can manipulate the data sets that are going to be put into the GPUs, because now you can bring to bear the full aggregate capacity and performance of that NVMe flash across all of the GPU servers and all of the high performance networking that's used to connect them. And the cool part about this is it's very, very easy to deploy. The machinery needed to have the compute nodes be able to supply that storage to the shared storage space is all built in to Linux. It's simply NFS. With the Linux kernel NFS server, you can deploy it literally within minutes, announce it to the sideband control plane that is the Hammerspace Anvil, and then voila, it can be used to host data distributed across the environment. So here we have an example. Oh yes, Eric, go
I
ahead.
was just going to say, I love that. This tier zero, I think, is not just one of the most clever things that a company's come up with in quite some time, but it's an excellent description because everyone understands tier one, tier two, tier three, and you're now opening up what I call the fastest path to compute, right?
Yeah, and that's really one of the key differentiations because people have done software-defined storage for a long time, and people have done hyper-converged infrastructure. Tier zero is very different. Tier zero is part of a continuum. It contemplates, or it's based on the notion of data orchestration, and that data is able to move across a continuum from tier one, even tier two or tier three, even across to other data centers, but flow all the way and get promoted into the GPU servers themselves. Now, this is a perfect example. This is a real world example of a customer that deployed some external shared storage, some NAS storage, and yet had 50% more storage in the GPU servers themselves than the shared storage that they had deployed. And when they ran out of space on the shared storage, there was a realization that, hey, we've got all of this trapped capacity inside of the GPU servers. So by using Hammerspace as the data orchestrator, and by using the standard Linux machinery to put a local file system, the XFS file system in this case, and export it using NFS, using the kernel NFS server, that now becomes available space for the orchestration platform and increased the capacity by more than double. Now, let's talk about this as a tier in the greater spectrum. This is not an island unto itself, although you can, and let me emphasize, you could have an environment with nothing but tier zero. It is perfectly capable of being the entirety of the storage. But we're assuming a world where you do want to have cheap and deep capacity that may not even be flash-based. It may be disk-based. It may be tape-based. You might have on-prem or even in cloud S3 object store that is part of the tiering system, and the data flows freely. So one of the first differentiations between this and software-defined and hyper-converged is that this is part of a complete data environment. It's not an island unto itself with all of the challenges of being software defined and being co-resident with the compute, limiting how you can scale the storage. Here you can scale capacity independently of scaling the performance tier. Moving to the next slide. So with this, you're able to achieve some immense performance improvements. And there is no place as exemplar of this as checkpointing. Let's take an example of a customer that has the need for 100 petabytes of capacity and a terabyte per second of bandwidth to serve 1,000 GPU servers. That would be 8,000 GPUs. With 128 terabytes of storage in each. Now, if you were to look at what it takes to checkpoint such a system, it is not uncommon for checkpointing to cause the system to stall for on the order of several minutes, hundreds of seconds. And checkpointing must be done every hour. Now, why do we checkpoint? Because things fail, especially when you have lots of components and burning really hot. So GPU servers can be less than reliable, and that means you have to roll back to a previous checkpoint and start over again so as to recover from a failure. Checkpoints are also useful to fork so that scientists can say, well, what if we trained from this point on using some different data? So checkpoints are also useful for some experimenting with alternate ways of training and so forth. But for this point, let's talk about it just in terms of work loss. And one of the key points is that if your checkpointing is done to tier zero, it can achieve the full performance of local access to NVMe while still being files on a shared file system. In other words, you get all of the benefits of local access with all of the benefits of it being shared file. And that allows the checkpointing to be brought down to mere seconds And because of that, you can do it more frequently and lose less data when you do have to roll back. And those two things compounded means that you're talking about recovering on the order of 10 to 12% of the GPU compute time. Meaning that if I have an environment with these 8,000 GPUs, you effectively have over 800 GPUs worth of more productive output by not sitting idle on the checkpointing, much less on the ingest or on the transforming of data that you might do through the system. Any comments here, Eric, or questions?
I mean, I just think this is really remarkable, and I know we're going to hear from Trond in a minute about going into the actual kernel itself, but basically you've opened up a super highway for data movement by abstracting out all the metadata of the files, where they are, what their names are, which of course
Yep.
facilitates orchestration, facilitates discovery. I mean, you can't orchestrate
Mm-hmm.
data that you can't find, right? I mean, just the
Yep,
discovery
indeed.
side is such a challenge, right?
Indeed. So yeah, the way the orchestration works is by housing all of the metadata in the control plane so that the data can be routed and dynamic, allowing data to move potentially even while it's being accessed. So let's move to the next slide here. Um,
And as you do that, David, one thing I think worth mentioning
mhm.
is, you know, we do have some massive customers in Hammerspace and using tier zero, but a lot of companies might look at this and say, well, I don't have 100 petabytes or I don't have 1,000 nodes. With our linear scalability, I think it's worth touching on whether you
Oh,
have
indeed.
10 nodes or 1,000, the benefits are the same, just in the appropriate ratio to nodes. But maybe just talk about that a little bit for smaller GPU environments as well.
Yeah, both on a capacity, proportionate capacity basis and on the performance basis. And the interesting thing is it scales with proportion because this is within the GPU nodes themselves. As you put in more GPU nodes, you get more tier zero performance in aggregate. And when you write checkpoints that are affinitized to hit the local media, um, I mean, it's logically been written to the shared file system, but it's physically being written to the local media on each node. You have perfect proportional scaling of performance. And because of the data orchestration, you can indeed scale capacity independent. You don't have to crack open the boxes to put in additional NVMe, although you can. So you have all of the flexibility of both, a shared storage, dedicated storage node environment versus the flexibility of, economizing by using the existing infrastructure that's already there. Literally not necessarily needing to deploy any shared storage whatsoever by just sharing the tier zero across the compute nodes. Now, let's get into more specifics here. If we look at how NAS architectures are built today, what you will see is why it's so important to move to parallel file system architecture. Here I'm depicting a NAS vendor that not supporting GPU direct. And you can see here how many times the data must be retransmitted across a bus, chip to chip, or across a wire to or from the networking. And in a scale out NAS systems, you have data nodes, the storage nodes at the bottom, and you have controller nodes that add the protocol, they add the file system. So the two boxes on the bottom are part of the storage, and the shared storage and the client obviously is your GPU server. So this is 10 data retransmissions. This is why NAS is not particularly well suited to serve GPU environments, but we get better by doing GPU direct. And you'll see in that top box a difference. The data is routed directly from the NIC to the GPU. So we depict that by taking the CPU root complex out of the path. And now we have gone from 10 to 9. So this is why all the hubbub around GPU direct. It allows the data to flow much more directly. You go to 9 from 10. Now, if you use NVMe over fabrics, then you can go from 9 to 8. Look at the bottom box, because now the data can flow from the NVMe out the network without having to go through the root complex there. So we've disintermediated the root complex, not just at the client with GPU direct, but down at the storage server with the NVMe over fabric technology. That gets us to 8. But all of this is just rearranging shares on on the Titanic, that whole approach is what is broken. Now, if you go to exotic file systems like Lustre or IBM GPFS, they use this approach that you see here. They take the control path out of the data path. They have a separate control plane. And that is indeed what hyperscale NAS does, but using standard NFS. So you get all of the benefits of this being plug and play NAS, but you get the performance from the HPC world. And as you can see, it makes a dramatic difference. Now we've disintermediated the entire controller node. What in the vast parlance is the C node versus the D node, the data node. So this is why hyperscale NAS is such a different architecture. But what is interesting about this is that the storage node and the client have nothing but off-the-shelf Linux. There is no software loaded there, unlike, say, a Lustre or a GPFS, where you're having to put software in your client and software on the storage nodes. And it's heavyweight, bulky, it has to go deep into the kernel. This is just using the built-in data path that's inside of the kernel that's made to move data zero copy and with RDMA capability. It's the NFS client to the NFS server. The entire data path, top to bottom, unadulterated Virgin Linux. Now, what that allows you to do is to fold it in on itself. So now the storage node is the client, is the storage node. The NVMe in the client is simply exported as NFS, and the client simply connects to the control plane and connects to parallel NFS to get the routing information. Now, if the data is located on a peer, then it will go out over the network to the peer using NFS and the machinery built into Linux. And it's extremely efficient because this is native code in the kernel. It's zero copy and it's capable of RDMA. So you don't have the massive overheads of hosting a complex storage node software stack. It's very streamlined. So you don't have noisy neighbor issues. You're not occupying them because it's zero copy moves, it's over RDMA, and very fast. But the cool part is when it's local, when the data orchestration system has affinitized data to the node or nodes using them, because it can run with multiple instantiations, one on each client, then you get the full performance of local direct access. And that's what we're going to talk about here shortly and have Trond talk about the work that's been done in the Linux kernel. So Molly, do we want to turn the time over to Trond here?
Yeah, I think so.
Yeah. Yeah, so on the face of it, the local IO patch set that was recently submitted to the Linux kernel is not particularly complicated. You know, what we're basically doing is allowing the client to identify the particular situation where it and the NFS server are co-located. You know, for instance, in the case where you're running a containerized system, you have a lot of different workflows happening in different containers, but all using NFS and all accessing their data through an NFS server that happens to be co-located on that machine. What this allows us to do is, rather than going out over the network stack, once the client has identified that it is actually co-located, it can talk directly to the NFS server, get authorized to access the file, and then basically it is given an ordinary file descriptor, you know, the way that your application usually receives. And instead of having to go over the network and go through the entire NFS server stack, it can then talk directly to the file system using this file descriptor, read and write the data directly without having to go through any extra hoops or impediments. So basically, what this allows us to do is to give ourselves native file system performance, and allows the client to reach, in our measurements, we've seen it sort of get up to around within, 5 or 10% of the ordinary native file system performance. We're still working on optimizing that. There's still work to be done to improve what's already in the kernel. But this is what we aim to do is really to give a set up a system that is fully fully performant, as if this was ordinary local storage.
Hmm.
Some perspective on that: with local NVMe, it is possible to achieve over 100 gigabytes per second of bandwidth and to achieve tens of millions of IOPS. And with this approach, that can be delivered through a shared networked file system, simply by promoting the data to be co-resident on tier 0. In other words, it acts as a cache, but this is much more effective than a cache. It not only delivers the performance of having data be promoted to be on the local high performance, but it's a true full instantiation of the data that can be referenced by peers. So cache can't do peer-to-peer serving like this can, and isn't a whole file where you actually get the aggregate reliability of now having additional instantiations of the data.
And we got a
And
quick
David,
question from
oh yeah.
quick question from the audience that I think is timely. An attendee is asking, is there a locking mechanism required for any of this, or is there no issue with data consistency integrity? I think the key is there is not a locking issue. Isn't that right?
That's correct. There's no need for anything beyond the standard PNFS authorization scheme, layout scheme, in order to ensure that the data is as consistently written as if it were being written over any other PNFS channel.
And that includes supporting multi-writer, multi-reader environments to the same file across nodes. And in our case, with multiple potential instantiations of that file sitting on multiple tier 0 nodes, or even on backend storage at the same time. One of the important capabilities that was added to the NFS 4.2 spec, the parallel NFS 4.2 spec, is the ability to do synchronous mirroring. And we today support up to 10-way mirroring, so you can have multiple instantiations across the environment, and each of those 10 instantiations can serve 1/10 of the client's asking. So you now have a way to do sort of a fan out aggregate even to the same file, having aggregate performance across nodes. And that's all made possible by the semantics available in the NFS protocol to manage concurrent reader writers across an environment. Good question.
Wow. Yeah, it kind of reminds me of when Google Docs came along and allowed multiple people to be collaborating on a single document at the same time. And I remember thinking to myself, oh my goodness, how did Microsoft get blindsided by this? Because what an astonishing improvement in collaboration. In the old days, you had to hand over the file and just pass it around the room and wait for someone to get back to you. And that causes tremendous delays in getting things done. Whereas if you're all in the same file at the same time, you can all see each other and collaborate. And this takes that capability to scale across multi-cloud, hybrid cloud. That's the other huge benefit here. You're overlaying whatever environment someone has, whether it's this cloud, that cloud, on-prem, who cares? It doesn't matter. You can see everything and get to it as fast as
Indeed.
is possible, right?
Let me point out one thing. While we're talking about this in the context of GPU computing, LLM, and other generative AI training type workloads, this has potentially even more direct applicability to virtual machine and container hosting. When you're hosting virtual machines and containers, you need to supply persistent volumes, block devices, for those. And in this case, you can actually have the VMDK equivalent files, the block device files, be positioned on the same physical host and potentially mirrored to shared backend storage or mirrored to peers. And the system will automatically do reads from the local instance and mirror writes, not just to the local, but to the off-world copy for reliability. So now you can have full read performance of local, write performance only needs to do one transmission off to shared storage or a peer. And for VM environments and container environments, that means you can get the extreme performance of local NVMe with a shared, reliable, persistent volumes from the file system. So this has major implications for traditional IT workflows, not just the GPU world.
And I think, David, would you talk a little bit about how you think about S3 and object storage and object-based workflows coming into this picture as well?
Indeed, yeah. So one of the other things that we're announcing today is that that Hammerspace now has the ability to serve and orchestrate object S3 object access, not just file. While we as a company first focused on file and parallel file, because it is the gold standard when it comes to the difficulty of implementing a full POSIX, random read write, we have now built a full consolidated platform where we can serve the exact same namespace as file and as object. And as I was talking before, if these are containers, you can actually serve them as block devices for those containers through the CSI plugin. So, but here we're focusing on the S3 capabilities. And in this world, the objects are files, are objects. The object name is the full pathed file name, the path qualified file name. And so you can create directories, you can create files, and you can then read those as objects in the object store. And you can even rename directories and shift around whole massive quantities of objects because it's not just a flat namespace under the covers, it's a full directory hierarchical namespace. We have also made the authentication coincidence, so you can hand out certificates and provide access, and those map to specific users. And all of the POSIX, ACLs, and SMB ACL capability of the environment are brought to bear. So you have a fully converged security paradigm, including, by the way, doing security ACLs or audit trail capability, and including doing worm and legal hold and object lock kinds of capabilities with the data in the namespace. But one of the most interesting things is that because Hammerspace has supported extended metadata, enriched metadata that can be user-defined or programmatically scraped and enhanced within the namespace, we have combined that with the object storage and the ability to have tags in object storage. So now the metadata that's read and written to objects through the S3 interface is metadata that's available and accessible through from the file system as well. And that metadata can be used to direct orchestration. Tags that are placed on objects can direct the service level objectives which those objects should be stored at, or the behavior of the object in terms of tiering, schedule, or other movement between data centers. So data orchestration can use enhanced metadata to help proactively position data where it's needed,
Wow.
both across the design spectrum and across the physical different data centers. And now those things can be controlled through the metadata that's accessible from S3.
That's crazy. I mean, would you say it sounds to me like you've enabled a dynamic, optimized, just-in-time information architecture. Is that about right?
That's a good way to put it. Is, I like to say this is a full decoupling of data from the underlying storage. And now it's storage interfaces in and storage interfaces out. So S3 and file and block storage in, and file, block, and object storage interfaces out. And that's why I like to say Hammerspace is not a storage company any more than VMware was a server company.
Hmm.
VMware conserved a server interface, consumed a server interface,
Right.
and presented as a server to the guest operating system. But they weren't a server company. They weren't Dell or HP, right? We're not a storage company. We're a data orchestration and single namespace, global namespace. This is the abstraction layer that allows data to exist independent of the very storage storing it and movable across any of it. And so this is a really important addition because S3 is commonly used in AI workflows. And because, you know, before having something like Hammerspace, the only way to really move applications to the cloud was to rewrite them to talk S3. People have assumed that S3 meant cloud or meant, cheap and deep. And this way you can have your cake and eat it too. You've got a parallel file system under the covers with the most extreme access performance, the most extreme low latency and high IOPS, and yet you can use it to get and put objects. And you can do that over HTTPS from the other side of the world. So the great thing about some of the capabilities here is that it's not just one object storage server. With Hammerspace, you can actually instantiate multiple separate S3 servers with different subsets of buckets or containers of buckets where you can create and delete buckets. So you can manage a world where you literally have thousands of S3 servers and separate parallel file system namespace to serve those. You can literally put a server and say, hey, this directory contains the buckets that this server is going to serve. And as you create or delete more directories in that, you're in essence creating and deleting whole buckets. Or they can come in over the S3 protocol and create a new bucket, and it is another directory in that same bucket containing directory. So very, very powerful capability to orchestrate S3 data and to manage the creation of, let's call them more like virtual S3 servers, from off of that environment. And
I
it's
mean,
all
does
tied
that
into Active Directory. Yes, go ahead.
yeah, I mean, does that mean that companies that have not yet refactored their applications to run in the cloud, if they leverage Hammerspace as part of their architecture, can avoid having to do that?
Well, just the fact that Hammerspace solves the scalability issue, which was the original impetus for
Mm,
making super simple storage. We
right,
dumbed down the file system so we could make it more cheap and deep and scalable for the cloud. But that meant everybody had to rewrite to use S3.
right.
With a true scalable parallel file system, that diagram with all the hops, by solving that, you can actually get, the ability to aggregate storage to that massive scale without sacrificing the performance, but actually getting aggregate performance and without sacrificing random read and write semantics because it's, true POSIX file system. So we would argue that had hyperscale NAS and data orchestration existed before, it might have preempted the need for dumbing things down to use, HTTP REST interfaces. But the fact of the matter is that's, water under the bridge. And people have already made major investments to rewrite
Right,
applications to
right.
do gets and puts over S3. And I don't want to be too disparaging. There are good reasons to use that. HTTPS is a great way to talk over the open internet at very long distances. and gets and puts of whole objects work well over high latency. So, there are places where an S3 protocol actually makes sense when you're doing things at a very large distance and over open networks. Those are things you wouldn't want to use a file system semantics for. And so this gives you the reach that S3 has, and allows things that are written to use S3 to continue to use that, even though the exact same data items without copy and without movement can be found in the exact same place, but as a POSIX file with random read and write capability.
Wow, and we have a very funny observation here I'll throw over at you. It threw me back whenever Attendees writes, "Maybe Hammerspace is to data processing what Magic Jack was to phone service back in the day." Remember the Magic Jack?
Yeah, yeah. Well, this is, I would say, a long overdue capability. As an industry, we virtualized the compute, again, back to VMware, and now we have a more refined way to do that with containerized microservices orchestration, like Kubernetes. Um, we virtualize networking, but virtualizing data from storage has always suffered. There's been attempts in the past, but it kills your performance and it kills your reliability because you're putting things in the data path, and it compromises that. It also compromises feature set. But here we have a way to add a sideband control plane and actually unlock the ability to aggregate performance in mass parallel. So this is the hyperscale NAS architecture is what has had allowed us to introduce data orchestration and to decouple data from storage, which has always been kind of that holy grail.
Hmm. Wow.
So Eric, as we kind of wrap up at least our bit of the presentation, I would just want to highlight that the advancement with our S3 capabilities, the S3 interface into our data platform and Tier 0 are all part of our 5.1 release of software, which was, bigger announcement than just those two capabilities. However, those are the two big ones. But I just want to highlight that in this software release, we've done a lot with our data platform to really optimize on performance, availability, those types of features as well. So you think about you're putting a lot of your data assets into Hammerspace, relying on it for your GPU computing. It being fast is certainly important. It's not just about the speed of latency and bandwidth that we talked about in some of the previous slides, but metadata speed. So the transactional part of the environment is moving quickly. Optimizing the data paths as data mobilities or data orchestration jobs are running. We're constantly optimizing those environments. And then a feature that we initially implemented in our environment at Meta in the Llama 2, Llama 3 environment around high availability and the ability to recover from, even pretty massive hardware failures have been added into this release. So things we did for Meta are now available to our entire customer base as well. So there's been a lot of other platform enhancements that I wanted to call attention to, in addition to the launch of Tier 0 and the S3 interface into our environment.
Yeah, and leave this slide up as we go through the Q&A here. We got a few more questions from the audience too, and I'm just kind of reminded of batch windows and my history in the structured data world and how the data warehousing took off. People got excited about it. Then they said, "Oh, I want this data in the warehouse. I want that data in the warehouse." Then you get all these batch windows, and it used to be overnight, and then there was too much to be doing overnight, and so you had to just wait for these little windows, and you have obviated the need for that kind of thing, right?
Indeed, one of the most powerful things about data orchestration is that data moves at the granularity of the individual file and is both proactive push and reactive pull, meaning you don't have to wait for whole
Right.
data sets to move. So Meta, for example, was able to move tens of petabytes of data from one system in one data center to another system in the other data center with literally the time it took to remount the clients, less than 5 minutes of downtime, even though it took days to even scan and pull in all the metadata, and it took weeks to move all of the data. Those things were happening in the background, and any specific thing being accessed, it would go and fetch that one on demand. So there was no waiting. And that's really at the heart of what data orchestration is. It's the ability to move things proactively and reactively at the finest granularity. So you're never artificially waiting for whole data sets to get moved and staged here or there or everywhere. And it's not coincidental that it's this same architectural innovations that containerized microservices orchestration, where you're taking the smallest, most granular unit of compute, the microservice, with the most lightweight encapsulation, a container, and that's the unit of orchestration. And here we're taking the most granular unit of data, the file, with the most lightweight encapsulation, its metadata, and that's the unit of what is orchestrated, so that you can automate it. You can really only automate it when it's no longer monolithic. It was very difficult to think about orchestrating, whole VMs with, whole, conglomerates of services. But as soon as you break it into microservices, now, and you can do that. And going back to your intro, moving to a world where it's a declarative model, declarative and automated, versus imperative or procedural, where you have to spell out the steps. In this world, you simply say what is desired in the end. What's the end game? What's the end state? What is your overall purpose, objective? And then everything is driven from that. Using that granularity and lightweight encapsulation, it allows the system to solve this massive multivariate problem, because now you can have every file could exist anywhere, right?
We got another good question from an audience member. Can this functionality be utilized for large-scale data migrations?
Absolutely. Yeah. One of the very powerful features of Hammerspace I was just alluding to, it's the ability to incorporate instantly by reference entire existing file systems or object stores and start serving it immediately, even while the metadata is being promoted and separated. The data can stay in place where it was. So that assimilation process can be used so that you don't even need a data migration to get it into Hammerspace. And obviously, once it lives in Hammerspace, it's orchestrated and it can move at the swipe of a mouse or based on just access demand. So yes, this can be used. And we had an insurance company that literally had hundreds of Microsoft file servers around their environment. They had acquired other companies, and over time they literally had hundreds of Microsoft file servers with tens of file systems on each of those. And with Hammerspace, they were able to go around and point it to those file servers and collect up all of it into a single namespace. And then with the swipe of the mouse and change of objectives, they could have the data uplifted and moved, and then they could decommission those original, hundreds of Microsoft file servers.
Well, and
with
that's right.
practically no downtime.
Right, that's the thing. I mean, I'm old enough to remember defrag your disk. Oh, I'm gonna defrag my disk, right? And they would show you the little schematic, like where it's like, oh, green, orange, yellow, all this stuff. It's like, oh, I'm gonna go ahead and defrag my disk, baby. Watch this, so I get better
Well, let me give you an
performance.
example. Let me give you an example of that. Let me give you an example of that. Some NAS architectures are log structured, and once they have written enough to need to do garbage collection, think of it like the problem with SSDs. Once the SSDs are full, you don't get that same write performance. Well, VAST is using a global log structure and has to do global garbage collection. So once it's written enough, it slams into the wall. In other words, you don't really get the performance out of the gate. And now you need to, one of the things is to be able to move the data off so you can reformat it back to fresh
Right.
and move it back on. So it's like defragging your disk, except for it's your entire VAST. Yeah.
That sounds like a vast problem that someone's going to face. We have another good question or an observation from an attendee here asking, so aren't iceberg tables doing the same decoupling of data from storage, a sort of management of
Indeed.
standardized tables?
Indeed. You can think of iceberg at the structured level of doing a similar thing. Of course, that's a database construct. You don't point applications to it and store files. So think of this as the layer underneath. This is the lowest layer where the data hits the media, the file system level. Every application is written to to, I mean, even the program itself is just a file on the file system. But then that program's data files, like the table files that the database uses. So this is lower level, and then it can host the relational database engines that make up your Iceberg environment. And now you can pick up the whole RDBMS and relocate it. So yes, you're correct. You can do this within the structured level if you want to be talking, SQL kind of stuff. But here we're talking about the more foundational level of, everything at the end of the day is a string of bytes in a file.
Right.
And that's this level. So it's a good analogy. And I've heard people talk about how, the difference between Databricks sort of at that relational versus a Snowflake. Snowflake is trying to end silos by being the one silo to rule them all, give your data to our service. I mean, and Frank tried very hard to say we're not a SaaS company, but it really is. And it's like we can be the siloed into all silos by having everybody use this one silo. But Databricks gives the connectors and stuff to be able to use things where they reside. And so that's, fundamentally a difference in approach. And you could say that's the difference. Databricks versus Snowflake is really kind of a difference here with Hammerspace. We are the abstraction layer, like the Iceberg, like Databricks, not trying to be a silo. I'm not a storage company. I'm not like NetApp trying to sell data fabric and keep everything in and on NetApps in every place, right?
Right.
This is come to the table with whatever you have, whatever
Right.
file storage, whatever block storage, whatever object storage you have, we will use that and we will accelerate access to it by putting a parallel front end on it. So there's an apt analogy. It is an apt analogy to think of the Iceberg and Databricks versus Snowflake.
Yeah, that's great stuff here. And there's so many other things I want to talk to you guys about, but we don't want to go too far over time. But I will say a couple different things and just comment on this. One, because you're overlaying all these different file systems and absorbing and adhering to their protocols, you can inherit governance policies, for example, on specific pieces of data. And then if you think about governance and risk management, especially in the context of large language models and trying to use generative AI and feeding it only trusted data and all that fun stuff, think about the fact that you are also solving the data copies problem because you'll see where the data copies are other places. So you can save money, save time, but also narrow the window for risk. Is that about right?
Yeah, we're not a security company or a governance company, but the single most impactful thing you can do to better secure and better govern data is to have it live orchestrated behind a single pane of glass, behind a single set of access controls, and with a single set of policy for governing it, and move away from a world where you're managing by copy, because that is literally scattering feathers to the wind. And you can't put those feathers back, right? So while we're not expressly focused on security and governance and those types of things, putting it in a global data environment that's fully automated and orchestrated, intent-based and so forth is really more impactful than, cataloging it after the fact.
Right.
It's like trying to put those feathers back in the pillow to go and gather up a catalog, which is immediately out of date, right?
That's amazing. This is fantastic stuff. Well, folks, we do archive all these webinars for later viewing. We'll be doing some more work with Hammerspace in the fairly near future. So send me any questions you want to ask on the next show, info@dmradio.biz. That comes right to yours truly. And like I say, this will be going up shortly. I think this is absolutely fascinating. I just love how deep these folks have gone. And I could talk all day to these people. But thank you so much for all your time and all this innovation. I think it's wonderful stuff. And we'll talk to you next time, folks. Thanks for joining the
Thanks,
briefing room.
Eric. Thanks
All
for
right,
having us on. We appreciate it.
Thanks, Eric.
absolutely. Absolutely.
Thank
Take